Okay. Maybe we should go ahead and get started, even though it's a couple minutes before, because everybody seems to be here. So maybe we won't run over into lunch today. So it's up to Jeremy on that, I guess. So,
no pressure.
So I'm going to actually, originally we thought about actually including a kind of tutorial or lecture on DMFT, on dynamical mean field theory, but that's not what this is. This is really just going to be an example of applying this. I guess what you could say here is that there are other forms of QMC other than what are being included in the school. And, but they, underlying them are many of the same ideas, and so once you get started, you can be open-minded into other approaches. One I'll mention is auxiliary field QMC, which I don't think is going to be covered, and which Shui Zheng and Henry Krakauer have built a all-electron code based on that, which is an interesting approach, I think, and it's not covered here. And another is, which is really not covered, though I'll have a few slides on it, is quantum Monte Carlo based on walking through Feynman diagrams rather than pushing electrons. Rather than pushing electrons or wave functions or density matrices. And so I'll say a little bit about that and show some results from that. This is really more of an applications talk than it is a tutorial in how to do another area, which would have taken really more than the amount of time available to lay all of the groundwork for it. Let's see. Okay, so a little bit of background information. Iron oxide is, I mentioned again on Monday, is one of those materials that DFT doesn't do a good job on. And so again, I guess Luke Schulenberger actually has done some diffusion Monte Carlo on FeO with me with QMC pack. And I don't remember if you used Casino also, but a little bit. And that work still, I could have put in some slides illustrating that, but I'm not going to today. But it's a metal, and it should be an insulator. Okay, so nevertheless, DFT does quite well with some of the energetic properties. So if you look at things like the magnetic moment versus compression, you see this high spin, low spin transition was first predicted with DFT. This is the magnetic moment versus compression. It's been seen now in experiments, and it's of a lot of interest in geophysics because it affects equations of state and elasticity very strongly and so forth. But nevertheless, DFT gives many energetic properties correct, even though it's not giving the ultimate electronic structure correctly. FeO is a rock salt structured material at room conditions. It's just like sodium chloride. It has partially filled D states. It's D6. And due to the localization of those electrons, it's an insulator, even though band theory makes it a metal. It's an interesting material from almost any perspective because it's a borderline material between a charge transfer insulator and a mod insulator, and therefore, even within the realm of correlated materials, it's kind of in a gray area. And there's also experimental difficulties in studying FeO. It's very important in geophysics because iron is a very common element in the earth, and there's iron present in almost all minerals, and so it's one of the most, so anyway, but it's hard to study in the laboratory because it has both 2+ and 3+ oxidation state, and one gets, for example, one tries to study FeO, instead wustite has up to 7% iron vacancies. And it's worse than that because it actually forms defect clusters, which have a lot of influence on its properties. Nevertheless, people have managed to make stoichiometric FeO under pressure, and all of the calculations I'm going to show you are based on stoichiometric FeO. The phase diagram of FeO has changed a lot in a short number of years. This is what we used to think. This was published in 1994 by Fei and Mao in Science, and it's still a good reference for seeing what the underlying ideas are in FeO. I said at ambient conditions it's just cubic rock salt, but if you go up in pressure, I feel like the mic is cut off. Is that right?
The battery may be down.
The light went off, and when I push it on, it goes off again.
But it was on a second ago.
Yeah, no, it seems to not turn on now, so maybe it's out of batteries.
Well, why don't you just speak loudly, you know?
Okay.
Use that mic.
Anyway, yeah, it's going to be all tangled up, maybe.
So it's not your mic, it's the other mic. So this one you can still use.
Yeah, okay. Okay. So if you go up in pressure at room temperature, it forms this rhombohedrally strained phase, which has a large strain. It's just like you took a cube and stretched it out along the cube diagonal. And then at very high pressures, it was believed to form this B8 nickel arsenide structure. And there were some high pressure and high temperature shock data that showed metallization. And it was believed that this metallization was the formation of this phase here. So that was the situation almost a decade ago in experiment. And I mentioned already that if you do band theory, you get a metal. And if you look at all of the different transition metal oxides, like simple oxides like nickel oxide, cobalt oxide, and so forth, they all have these high spin, low spin transitions within DFT. And you can understand them very straightforwardly just from the band structure. So it seems like DFT is not doing a terrible job with the band structure, except somehow it is, because if you look at the details of the band structure, you see that there's no way to open up a gap. It's not just a numerical problem that the gap is predicted to close and it really should open. You see there's no way to open a gap, and in fact by symmetry there's no way to make a gap, because if you think about D6 material that's high spin, it means that you have by definition an open-shelled half occupied orbital, or partly occupied orbital, as I'll show in a second. Yeah, here, I'll show you right here. So this is the configuration for low pressure. It would have a moment, ideally, of 4 Bohr magnetons, and you would have 5 up electrons and 1 down electron. And of course, in the cubic environment, the T2G state is triply degenerate. And so you can see right off the bat that it's got to be a metal, because you have this degenerate state occupied, which could hold 3 different electrons, but instead it's just got 1 in it. So that degeneracy means that it's going to be a metal no matter what. So band theory, any kind of band theory, no matter what density functional you use, will always make cubic FeO a metal, except it's an insulator. Okay? So this is kind of the definition of a strongly correlated system, something that, it's not just some small inaccuracy in band theory or even large inaccuracy in band theory. It's just that the band theory is completely wrong. It doesn't act like bands. Okay? The electrons are somehow localized so that they don't so that you don't get any metallic behavior. Now, at high pressure, it goes low spin, DFT says. And so this is the idealized low spin configuration, would just be 6 T2G electrons. And so I want to make a case here that we want to think about orbital occupancy in this transition as well as magnetic moment. Because if we look at high temperature, or even at room temperature at 0 pressure, FeO is paramagnetic. So there is no net moment on any of the iron atoms. But what is happening is that these moments are disordered at low pressure, but it still has this high spin like orbital occupancy, so like 4 T2G electrons and 2 EG electrons. And so even in the non-magnetic system at high temperature, there's still an orbital ordering which changes at high pressure. So this is kind of background information of what we expect to see in FeO under compression. Okay, so what kind of methods are there to study it? So one of them is to do diffusion Monte Carlo. And like I said, Luke has spent quite a bit of time doing diffusion Monte Carlo calculations on FeO. Now, one of the issues with diffusion Monte Carlo is that at least everything we've learned about here has been basically zero temperature. So we would then use DMC to study the ground state of FeO. But that's going to be different than the high temperature paramagnetic state. So we would be studying with DMC the antiferromagnetic ground state and how that changes with compression. I want to talk here about the paramagnetic FeO, which is important in the Earth and at high pressure. And so we need some other kind of method. One could imagine doing path integral Monte Carlo, I guess, in principle, except that these temperatures are low. And so to do room temperature with path integral Monte Carlo with electrons is forget it, Burckhardt says. So though I have a problem with that. So isn't it basically linear? And I guess it's going as 1 over t.
We don't have good nodes.
Okay.
That's the fundamental problem.
Okay. So it's not just a matter of running longer and on a bigger computer. I mean, it's some fundamental issue.
Well, there's been so little research on this. I would disagree with Burckhardt that, it's pretty much, nobody's tried that much.
Well, we cannot do it at the moment.
Okay, well, this is a wide open area. So any of you students out there looking for something, if you do this, you'll make a name for yourself. So that's for sure, right? Okay. So I'm going to talk about a different approach, and like I said, it's not a tutorial, but it's enough just that I would give in kind of a standard kind of departmental seminar or something like that to give you just a flavor of it. And so basically the idea is to use what's called dynamical mean field theory, and I'm going to give a little bit of justification of what it is and a little bit of explanation and how we applied it in this case. This is work I'm doing with Christian Hawley at Rutgers University. So let's just think about a normal magnetic system. So if we think about a magnetic system that has up and down spins, like a Ising model or something like that, we can think about solving a Hamiltonian that looks something like this, okay? So with up and down spins on the lattice. And we can replace that in the classical mean field theory with the idea that a single spin is just going to interact with a mean field. So this is classical, mean field theory. And then the interaction with the rest of the field from the rest of the system is dependent on the average spins of the whole system. So that's how you get the feedback loop in regular mean field theory. And so that field from the whole system is called the Weiss field. And so that's classical mean field theory. So what is dynamical mean field theory? It's the same kind of idea applied to the electronic problem. And it's exact in the limit of large coordination. Just like mean field theory here is exact in the limit of infinite dimensions, so is dynamical mean field theory exact in the limit of infinite dimensions or infinite coordination. And the idea is that we're going to take some kind of subsystem, quantum subsystem, and we're going to treat it exactly or really well, whatever. We're going to include correlations. And then we're going to let it hybridize with the rest of the system in a self-consistent way. So we're only going to solve a correlated problem in some small system. In my case, it's just going to be a single iron atom, single iron ion, and then let that hybridize with the rest of the system in a systematic way. The way it hybridizes is through this effective Weiss field, through this effective interaction with the bath of the rest of the electrons in the system. So again, this is another picture of the idea, except a little bit more detail, just a little bit. So we're going to use basically DFT to solve the band structure problem. We're going to use DFT for the crystal. And we're going to use some kind of complicated many-body impurity solver for the iron atom. And we're going to put the two things together. So, and the way we're going to put them together, I think, is shown here. Yes, okay. So basically, we can express the normal crystal problem, the normal DFT problem, as a Green's function, which is related to the normal Cohen-Sham Hamiltonian. And this is the overlap matrix, and this is just kind of the normal problem that you would solve.
I have a question.
Yeah.
Can you just say briefly why you're restricting yourself to a single iron atom and treat this with this method, and you couldn't take a whole unit cell or a crystal?
Oh, well, in principle, you can take a cluster. So people have done that, but the problem goes up exponentially as you go up in the number of electrons that are included in your correlated cluster. So it hasn't been done for the number of electrons that would be in one unit cell of FeO for anything yet. Okay, but in principle, that's just a minor detail if you ask the practitioner. So in principle, they can use any size, correlated subsystem they want, and you can converge it until you have, a cluster that's, as big as needed to include all correlations. So then you would basically have, maybe someday people will be doing that. But right now, just operationally, we can only do it for this number of electrons.
You can get at most 5 states now, or you can represent at most 5 bands, I guess. Or
well, no, we can do all the D states, so that's 10. Okay.
10.
Yeah.
Okay.
So we've already come a long way.
Yeah.
So yeah, some years ago you couldn't even do all the whole D manifold. Now people can do the whole F manifold. I mean, and F plus D even people are starting to do. I mean, so things are progressing. People are getting more efficient in their codes and parallelizing them better and writing them on larger and larger machines. So I mean, but nevertheless, you get a huger and huger Hilbert space that you have to deal with, and you have to deal with it. And if you want to do it exactly,
you have to exactly diagonalize the unit cell, right?
Well, whatever your cluster is, you have to exactly diagonalize. And so in principle, if you want to choose which states are important, you could throw out ones. Like if you say only T2G is important, then you could leave out the EG. Maybe you could start doing bigger clusters. But anyway, this is just computational limitation. I mean, in principle, maybe someone will find a higher level, a Monte Carlo approach to dealing with the bigger Hilbert spaces instead of doing the full thing or something like this. So I mean, I think there's lots of grounds for improvement in this area, in the future. We got a long way with this local approximation, as I'll show you. So I mean, it's not like the end of the world here. I mean, even though we are making an approximation, it seems like it's a pretty good approximation. Remember, DFT is not so bad all by itself. I mean, it's not giving the right symmetry, the right localization, and so forth in FeO, but the energetics aren't that bad in FeO. So we're going to start with that as the kind of zero-level approximation. But the difference is we're going to add to it a self-energy, which is going to come from this correlated subsystem. So this is the normal DFT problem over here, and we're just going to add a complex self-energy, which we have to get from somewhere else. And so this self-energy will change, of course, the spectrum altogether. Okay. Another detail here, all these calculations are done on the imaginary axis, and then you have to do analytic continuation to get any real property. Just like we used in QMC, we talked about doing diffusion Monte Carlo in imaginary time and path integral Monte Carlo in imaginary time. For the same reasons, we work in the imaginary axis here. Okay. Then we also solved this impurity problem, and you can think of this as a black box, and I'm going to show you what's inside the black box, but a lot of times people think about this as a black box to solve the correlated subsystem. So there are different solvers with different levels of approximation, but what we're doing is basically solving it exactly with quantum Monte Carlo, but this can be done at different levels of approximation. And then this is maybe the important bit, because these two parts existed separately for many years. And I always tell this little anecdote because it's fun. But years ago, I was at this superconductivity meeting in Stanford, and a group of colleagues, and I was at the Naval Research Lab at the time. We sat down at a banquet where Phil Anderson was giving the keynote address, and we sat down at the table. And we introduced ourselves to the other people at the table, and they said to us, "We're many body, physicists. What do you do?" And so, one of us said, "Well, we're band theorists. So they looked at each other, they picked up their plates, and they moved to another table. So this was the state of the field, like 20 years ago. But now band theorists and many body physicists are working together, and that's really expressed with this equation. Okay, so this is the equation of cooperation, if you will. Okay, so on the left-hand side of the equation, you have the Cohen-Sham problem, except with a self-energy added to it, and you're going to project from that problem onto this localized quantum impurity problem. And then over on the right, you have the quantum impurity problem that you're going to do with some kind of impurity energy levels and some kind of impurity self-energy and some kind of hybridization with the rest of the states in the system that are over here. And you're going to have a self-consistency between these two sides. So this is kind of the equation of cooperation. And so what we do in these calculations with Christian Hallé is a fully self-consistent solution to this problem. Now, one of the problems in the DMFT field is that you'll find many papers on DMFT, and to an outsider, they all kind of look the same. But really, they're very, very different. So 99% of the papers in this field are non-self-consistent. So people just, they don't really have this equation, or they only iterate it once or whatever. They don't iterate everything to full self-consistency. But what we're doing is everything is fully self-consistent. The charge density, the chemical potential, the impurity levels, hybridization, self-energy, everything is done self-consistently. And we use a really good technique both for the crystal problem and for the impurity problem. We use the LEPW method for the crystal part, which is an all-electron, very accurate method, no pseudopotentials, so we don't have to worry about pseudopotentials. And then this impurity problem we do with continuous time quantum Monte Carlo, and I'll show a couple slides on that, though really not going to be explaining enough about it to really understand it. So this is really the impurity problem. Basically, we have some kind of free energy functional, and the free energy is a functional here not of the density, but of the many-body Green's function. Okay, so if we take the idea of density functional theory and we just go another step, that's how we get to these many-body approaches, is we take a functional of the Green's function rather than a functional of the charge density. And then we can carry everything through in the normal sort of way, and you end up with an action or a partition function that needs to be solved. Here's the action for the quantum correlated atom. And then there's some hybridization between the atomic states and the rest of the crystal. And the correlation, hybridization is represented by this delta here. So basically, what is being done then in the impurity case is one basically sums over all possible Feynman diagrams on the correlated subsystem, and one does this with quantum Monte Carlo. And so basically, you can express this partition function in terms of a path integral, basically, that can be represented as a QMC-like process. Okay, so basically, it's metropolis sampling over Feynman diagrams, and you can show that this is an exact solution to the problem when converged. And basically, what we can think of is happening in this simulation is we can think of the imaginary time as being a circle. So we start at 0 and go up to beta. And each one of these vertices here, something happens. So like electron hops from one orbital to another orbital or into the crystal or something like this. And so basically you add new vertices to this diagram, and the vertices should really have different colors depending on what orbital is being occupied or not occupied and so forth. And then they're either added or destroyed and accepted or not accepted based on a metropolis-like probability.
Are you supposed to have lines that are not connected there?
No.
Okay.
There should be another line, yeah. This is a simulation in progress or something. Well, you can design it in such a way that there's no sign problem, probably.
Sometimes,
okay.
Right?
Yeah, okay. So there's no, as far as I know, mathematical proof that one doesn't have. Well, actually, maybe there is. There are some cases where you can prove.
They don't cover every.
Right.
Well, they certainly don't cover every model,
right.
but.
Right. The code will allow you to put in a problem that has a sign problem and get garbage out. Okay, so I've done it before. So
I think typically the bath stabilizes the sign, right?
well, typically, but that's if your matrix is strongly diagonal and so forth. So if you have a large off-diagonal elements, it can turn out to have a sign problem. So this is actually, in some sense, a frontier question. I mean, I don't believe that there's proof of which system. I mean, there are sub problems that you can prove have no sign problem, but basically, you'll know if you have a sign problem because you'll get garbage out. Okay, so So the self-consistency problem is very much more complicated than in the case of normal DFT. Normal DFT would just be like a loop like this, and you would just iterate it until you had self-consistency. You would do the core states and solve the Cohen-Sham problem and calculate the new potential and iterate. But we also have the impurity problem, which is a whole separate problem. As we change the different bath levels and the hybridization, as the bands move around, we have to iterate the DMFT problem and then an overall loop with the DMFT and the DFT. So it's a multi-level self-consistency problem, and it's highly nonlinear. So if you start out with a bad starting guess or something, it just won't converge to anything. Okay, so you have to kind of learn to know what you're doing before you can get any decent results out of this. And to give you an idea of the complexity of this and why this wasn't, let's say, just done before, is that you can't just write it down on the back of an envelope or something like that. When you do these simulations, you find that a typical simulation has on the order of 200 kinks at room temperature, in that, in terms of that means that you're including up to like Feynman diagrams of 200th order, okay? So you could imagine trying to solve those integrals, by hand. It's not going to happen, right? So, but this is an approach where you can, through Monte Carlo, basically solve that problem, okay? And so, so we can, after the fact, see, what kind of diagrams were included and which ones were not. Okay, so I was doing those calculations and getting some interesting results, and then one day we had a postdoc from Japan come visit us, and he was coming to give a talk about something totally different, but he came to my office and he said, this is Kenji Ota, he said, I have some results that you might be interested in. And so he basically showed me these results. So this is for FeO, these are experiments. And what he showed is that the resistance, which is what he was doing, his experiments measure resistance as a function of temperature. Initially it went down, and then it seemed to kind of go flat. But then as he went up in pressure, it looked like the resistance went up with temperature rather than down. So in an insulator, the resistivity tends to go down as you raise the temperature because you start exciting states above the gap. And in a metal, the resistivity tends to go up with temperature because you have more and more scattering. So he said, it looks like I have an insulator to metal transition at high temperature and pressure. So I pulled out my DMFT results, that were sitting right on my desk on top that I'd had for like a year, and I hadn't published them because I didn't know whether to believe them or not, that showed exactly the same thing. So we decided to write this paper together. And this is not actually what I showed him, but this is what I went back and I computed the full density of states you have to do analytic continuation to do this. And see at low pressure and temperature, there's a band gap. This is the density of states. And then as you raise the pressure and the temperature, you get something that looks like a good metal. And so he went back to compute the actual resistivity from his experiments. So he needed to look at photographs and figure out exactly what the geometry was to convert resistance into resistivity. And I went back and computed the resistivity or the conductivity from the DMFT calculations. And this we kind of sent to each other, this is the two graphs we sent each other put together, over email. And showing that we really get a perfect agreement between the experiments for the resistivity, this is the conductivity, versus pressure, and this is at 2,000 Kelvin, compared with experiments. So it looked like, the theory, DMFT plus DFT, really is giving the right prediction of this high pressure metallization. So one of the things that we can do with theory, that you can't do so easily with, and this was published in PRL, I guess last February. So one of the things you can do with theory, that's hard to do with experiments is figure out exactly what's going on. So the experiment showed that you got this high pressure, high temperature metallization in FeO, and it really wasn't what was expected. What was expected was to see metallization under pressure, but not that it would be temperature dependent. In fact, many people told me, there must be something wrong with my calculations before the experiments came out. And many people told the experimentalists there must be something wrong with their measurements. And so this is an area where you can do theory and experiment and you both back each other up and then have, enough courage to actually publish it.
Well, the surprising part is that there was no structural transition associated.
There's no structural transition at all, right? So the original idea was that in the original shock measurements, that the metallization seen there, they thought that it was due to this transition to this nickel arsenide structure. It seems now I'll show you that it's not due to that. It's due to this metallization, which is isostructural. So that study had not had any X-ray measurements associated with it. So we could also, from theory, look at exactly what's going on in this transition. First of all, what I show here, this is again in paramagnetic cubic FeO, the T2G and EG occupancies that come out of the DMFT calculations. And you see at low pressures shown here on the right, volume here on the left, that you basically have a high spin situation, which with the occupancies that you expect to see at high spin D6. When you go up in pressure, what you see is it basically becomes a low spin with only the T2G or mostly the T2G orbitals occupied. But the interesting thing is the region where this metallization is occurring is where you start to see this transition start to occur. So this is the region where metallization occurs. You see it's not occurring all the way over here. It's occurring right at the beginning here. And also what you see is that this high spin, low spin transition is not what's driving that metallization, because these two curves here are at two different temperatures, 300 and 2000 Kelvin, and they're not very different. So it's not that the high spin, low spin transition depends on temperature, which is another thing that people had hypothesized. Rather, it seems to be fairly temperature independent. But what is important is the onset of this beginning of this low spin state. So we can actually look at the spectral function. So I showed you band structures earlier. So in band structures, you just have, and it would be wonderful if we could figure out how to get these kinds of things out of DMC or something, but I don't know any way to do it. So this is one of the advantages of this sort of approach, is that you can actually directly compute the spectral function, and this is something that can be directly measured in experiments. And in a normal band structure that you see, you just see delta functions, right? You just see lines. And so here, though, there's actually a width. So it's a function of frequency and wave vector. And so you can see the oxygen P states here are pretty sharp. So they're pretty uncorrelated, which is what you'd expect. But the iron D are very diffuse and incoherent. So you see the iron D states are this mess out here. They don't look like bands at all. And here's the band gap, or the gap, at low pressure and temperature between here. And what happens when it metallizes, you see basically this gap just collapses. It doesn't look like people used to think of as what you would expect to see at a kind of Hubbard transition. So we can actually go a step farther with this and look at what many body states are included in the solution. And so here is really a grounds for doing multi-determinant QMC, which I hope to do at some point soon. So at low pressures, what you see, this is at low pressure and low temperature. Oh, there's two temperatures shown here, both 300 and 2000. They're not real different, though. There's basically 1,000, I don't remember exactly how many, but there's so many body states that are possible to be occupied. Most of them have no occupancy at all. These three peaks are basically D6, D7, and D5. And then you see that there are a few different states that are occupied. So the number of many body states that actually have any weight at all is very small. Though you see it isn't that there's 100% in one state. See, this shows you the amount. You see the most occupied state is only 14% occupied. So even at room conditions, you see there's different, you're not going to probably get the right answer doing a single Slater determinant, basically, because even if you do DMC, because you see there are different many body states involved. When we go to high pressure in that region where we start to see metallization at high temperature, what we see is that there are now both low spin and high spin many body states involved and occupied. And we also see that there's a very strong temperature dependence in the occupation. So the green versus the red are at two different temperatures. So our argument for what is driving this metallization is really fluctuations, both thermal and quantum fluctuations, but mainly thermal fluctuations between different many-body states. So in the end, we get a phase diagram these are all experimental points, and showing that now at high pressure and temperature, there is this metallization line, and that this nickel arsenide structure is actually over here, actually not geophysically relevant because temperatures in the Earth follow a line that goes up through here through this rock salt metallization. So this is important in geophysics. I didn't put any slides on this because it's not a geophysics meeting, but geophysicists are very interested in this because if you have a metallic layer in Earth's mantle, it greatly changes the way Earth's magnetic field propagates to the surface and so forth. So anyway, this has been very popular on the web. So it's been quite a while ago I did this, but I found 1.5 million hits on the web to this new kind of metal. But the only thing is you also find a new kind of metal, rock groups. So some of those 1.5 million are those as well. Okay, so I'm going to give Jeremy plenty of time. So, and maybe there's some discussion, but the interesting points I think I want to pull from this is there are many different nooks and crannies of the QMC field. One of them is in this DMFT, DFT area where you can use temperature, and it's a crucial parameter. So if you spend your whole career studying zero temperature properties, you may miss out on something. We think that the metallization in FeO is due to fluctuations between high and low spin states. In principle, one can now use this idea and try to develop simpler models that have this behavior as well. We find that self-consistency is crucial. When I do these calculations in the kind of standard non-self-consistent way, I don't see the metallization. So it's only coming about in the self-consistent process. And we got very good agreement with experiments. Okay, thank you.
DMFT and the dynamic field theory, I think actually there should be time machinery, there's some enumeration of the important parameters.
I'm sorry, not hearing the question. Good.
Okay, so I guess actually during those DMFT and the dynamic field theory combination, there should be time machinery, there's some enumeration of your important parameters.
Renormalization of the parameters. Yeah, well, which parameters do you mean? Like the, you mean like the U and so forth? Or?
Yeah, that's actually what I computed.
I'm sorry, I want to answer, but I can't hear the question.
Maybe some enumeration in your correlation function or some kind of interactions probably when you treat actually your system and then the other environment.
Okay, well, there's no like renormalization of any of the parameters that I talked about. I mean, so everything's just done self-consistently, and things will renormalize on their own in the sense that the impurity levels and the hybridization are allowed to change as a function of the process through that self-consistency condition. What is true, and I didn't talk about, is there's two things I didn't talk about, which are important. I mean, one is that we do have to put in essentially a Hubbard U and J as input into these calculations. And I have checked, and for this particular properties I'm computing, they don't seem to be sensitive to that. So as long as I make the U large enough so that I get an insulator, I see the same behavior at about the same conditions, which shows it's not really driven by the U. Once you open up a gap with the U, it's enough. It does seem, so it's really more of a charge transfer sort of situation here where it's really the hybridization with the PD hybridization that's most important, and that's coming out of the DFT part, which seems to not be too bad. The second part is that DFT already includes correlation, so we have to do what's called a double counting correction to correct for that. And so people have settled on a way to do that, but it is kind of an ad hoc correction. If you don't do it, you just get garbage. So I mean, and the result that you get, can depend on that. But I didn't do, an exhaustive study of different, double counting corrections. They're already in the literature, and this is the one that seems to give the best agreement with experiment. But it's not fundamental. So these are approximations. So even though we're doing a really good job with each of the parts that I talked about, there are some parts that are approximate, other than the fact that we're making this local approximation. If I kind of summarize then the approximations that are inherent, we've got a local approximation to the correlations. So we only have, single site correlations. The second thing is we have to do this correction to the LDA part to try to correct for the part of the correlations that's already included in the LDA. And then the third thing is that we have these parameters, this U and J, which are input into the model. Now, in principle, those can be calculated from constrained density functional calculations. In fact, that's been done, and that's the kind of parameters that we're using. But if you had a result that was very sensitive to the value of those parameters, then I guess you would have to publish, a table of your results as a function of U and so forth in order to have some kind of, understanding of, what the dependence on your input parameters was. But those are really the, I hate to say only, but those are the main approximations that are inherent in the calculation.
So at the end of the calculation, you have a density, and
Yes.
You have a new set of orbitals as well.
Well, you have, you have a new set of, say, single particle orbitals, yes.
So can you run QMC on those and see?
Yeah. That's the idea, is to use the, pick out these, occupied many-body states and do multi-determinantal.
But, have you tried that at all?
No.
Does that provide a better wave function than what you had with the DFT originally?
Well, it should. Okay, first of all, what's already been done to some degree, and in fact Luke did this in his study of FeO, is I didn't talk about it, but there's an earlier level model called LDA plus U, which is a static approximation. It doesn't include any multiplets, so Luke did that. He used LDA plus U wave functions as his trial functions within QMC. So you could do the same thing here. The only thing I would say here is that now we have multiplets, so you would have to do the the multi-determinantal. Just picking out the state that has 15% weight and doing a single determinantal DMC probably not worth doing.
You still couldn't say whether or not that wave function was better than the same one from...
Oh, well, you could do VMC and you can compare wave functions. Sure. I suspect that it wouldn't be any better than doing the LDA plus U if you just did a single determinant. I think probably LDA plus U is kind of the best, single determinant approximation, consistent with DFT, It's kind of like doing a screen Hartree-Fock calculation.
Produced by OCE Atlas Digital Media at the University of Illinois, Urbana-Champaign.